Hello, physics students. This is Mr. Steinerson, and in this example, I'm going to walk you through a sliding to stop friction problem that at first glance seems like it might not be possible to solve with the information given. So let me read this through for you, and it involves a worker that shoves a box, lets go of the box, and the box continues to slide to a stop after 2.5 seconds along a factory floor, and it takes 5 meters for it to come to a stop. Okay, so we know the question would ask things like, what is the coefficient of friction between the box and the floor? Now, at first glance, you might be asking yourself, well, I know coefficient of friction, and in order to solve for coefficient of friction, I'm going to need the frictional, I need the frictional force and also the normal force. And in order to find normal force, I'm going to need the mass because that's related in this case to the weight. That's horizontal force. So anyway, I have to figure out a way to do it without those variables. And often problems like this can be solved if you map them out symbolically before you put any numbers in. So I'm going to walk you through that, and we'll take a couple examples here to kind of figure out how we can solve this using some algebra and symbolically first. All right, so first things first, let's map out our free body diagram with this. And I'm going to draw down the forces. The first force is the downwards force due to gravity, so Fg. And I also know that there is a normal force that's equal and opposite in this case. So this would be the force normal. And there's also, since it's sliding to a stop, let's just say it's moving to the right, I know that something's slowing it down. So there must be an acceleration horizontally, and that's being caused by a unbalanced or a net force. Okay, so let's think about that for a second. There must be a frictional force acting, and if it's sliding to the right, it's going to be opposing the motion. The question I always want you to ask yourself is, does another force exist in that horizontal direction to maintain the motion? And the answer should always be no. When it slides to a stop, there's no rockets acting on it. There's no fan. The person isn't running behind it, continuing to push and apply a force. The only force acting is the force of friction. All right, so let me give you another example what this might look like. So let's just say we take an example here. I'm just going to draw in some forces. Let's say we have a downward force of 3.6 newtons and an upwards force of 3.6 newtons. And then we have a sideways force of, let's say, 5 newtons. By glancing at this example, you could probably tell me really quickly what the net force is, right? I know the 3.6 upwards and downwards would balance each other out. They're in equilibrium. However, the only force that remains is that horizontal force of 5 newtons. And it would be, in this case, the net force. So force net in this quick example, we can all agree, is 5 newtons. Okay, we're going to take that same idea and apply it to our free body diagram over here. Look carefully at the types of forces that we have, and the net force, or for this example, has to be the force of friction. And it's only going to be the force of friction because there's no other horizontal forces acting. Okay, so that's going to be a really key thing to keep in mind. Remember, there's no force when it's sliding to a stop. There's nothing else pushing on it. Friction is the only thing that's causing that acceleration to happen. All right, so let's start out with that equation that we know then. I know that the force net, in this case, is equal to any mass times acceleration. Okay, that is our general second law equation we can always come back to, right? Well, if I look closely at my diagram, I know that the force net is really coming from the force of friction. So I'm going to substitute that in. Force of friction is equal to the object's mass times its acceleration. All right, let's go one step farther. Thinking back to what we know about our definitions of force and friction, hopefully you recall that the frictional force is equal, we have an equation for it, we can solve for it. It's equal to the coefficient times the normal force, okay? Where the normal force is the force perpendicular to the surface. Well, I can take this information and I can come back to the problem here. I'm going to plug in what I know for the force of friction, which is normal force times the coefficient. I'm going to plug that right in for force of friction. So instead of writing force of friction, I'm going to write mu times force normal. And that is equal to mass times acceleration. Okay, now we're getting close. There's one last relationship that we have to remember, and I want you to think back, how does the force that's acting in the force normal, this perpendicular force, and the force gravity, how are they related to each other? On a horizontal surface, they're always going to be equal. Okay, so that we can use that as well, because I know if the force normal is equal to the force gravity, I know an equation for force gravity. That is equal to m times g. All right, let's substitute in what we know now. So I know we still need to solve for their coefficient. However, force normal is the same as mass times gravity. So I'm going to substitute that in. And that's equal to mass times acceleration. Now, hopefully you're seeing symbolically that the mass shows up on both sides. Therefore, it's going to cancel out of our equation. So this and this really disappear. So then I'm left with a relationship where the coefficient times the acceleration of gravity is equal to acceleration of the object. All right, now I can solve this even further, and I can just set this up so that we can use it to solve for our coefficient. We're going to take the acceleration of the object divided by the acceleration of gravity. All right, for this case, let's be really precise. Let's use g is equal to 9.81 meters per second squared. We'll come back to that here in a second. Now, in this problem, they don't go and tell us what the acceleration of this object is. I mean, that would be great. However, they do give us some information that we can use to solve for it. So I'm going to need to use the time it takes and the distance up here to help me find that acceleration. Now, there's some real clues here. One of those is that it's sliding to a stop. Okay, so then we know that the final velocity has to be 0. We know the time it takes, and we know the distance. All right, so I'm going to write down some of those variables that we know already so we can figure out, hopefully, what that acceleration is and plug it back in. All right, so to find A. Now, you're also going to be tempted in problems like this to jump right to equations that will solve for A. All right, so let's think through this a little bit. We know the final velocity is equal to 0. We're not sure about our initial velocity. We know the time was 2.5 seconds. And we know the distance that it accelerated through, this is a uniform acceleration, was 5 meters. We don't know the acceleration. We need to find that. That's what we're solving for. All right, now, like I said, you might be tempted right now to jump in, try to find an equation that can just solve for A. Unfortunately, I'm going to tell you that you're not going to find one. So we make this into a two-parter, 2 steps to solve this out. The first thing we're going to want to do is actually solve for our initial velocity first. All right, so to find VI, we can substitute in all those equations that we've already kind of known and have been using in the past. All right, for example, I know that the distance traveled is equal to VF plus VI, all divided by 2, times the time. Okay, taking that average velocity and times the time to figure out the distance traveled. From here, I can rearrange and I can solve for VI. Okay, so I know then that VI is going to be equal to my VF minus 2D over T. I'm just rearranging that equation real quick. Now, I already know that the final velocity is 0, so my VI is going to be 2d over t. Substituting in what I know, 2 times 5 meters, so 10, divided by 2.5. So I get an initial velocity, 10 divided by 2.5, of about 4 meters per second. Okay, now that I know that information, I can work backwards, and now I can find A. And I'm going to use I'm just going to use an easy equation for this because I know that VF is equal to VI plus A times T. I'm trying to solve for A, so now I can simply plug in what I know. The VF goes to 0. That's 0. My velocity VI, move that over to the other side, is now equal to A times T. And now I can substitute in my 4 meters per second is equal to A times 2.5 seconds. Solving for A, I'm going to end up with about 1.6 meters per second squared. Okay, so folks, that's the number that I can now take and plug back into the acceleration up here. So let's do that. I'm going to plug in my 1.6 meters per second squared divided by 9.81. So that's the acceleration of gravity. And that is going to end up giving me my answer for my coefficient. All right, so those are the things that we're going to take a little close peek at. I'm going to calculate this out real quick here. So 1.6 divided by 9.81, that gets about 0.163. Remember, coefficient has no units. So at this point, we're done. A little bit that got us there, if you remember, our free body diagram helped us identify that friction was the only horizontal force that is equal to the net force in this case. Net force is always equal to mass times acceleration. And once we figured out that, we can symbolically substitute in what we know, that the frictional force is the same as the coefficient times the normal force, that the normal force is mass times gravity, and that we can cancel the masses out, and then we solve for mu. Hopefully this helps with these problems that don't seem to have all the information that you need to solve them, like a situation that we just went through. Thanks, and have a great day.